Well, thank you very much for inviting me to give a talk. And as mentioned, I'm currently in Perth, Australia, and it is going to go into the wee hours of the night, which I'm looking forward to. So I'll be presenting work that that I did with collaborators with my team under the director, Professor Marcus Kraft. We'll be talking about carbonaceous nanoparticle formation. So we're going to go into much smaller particles. And I just wanted to show the group, the computational modeling group from the University of Cambridge, that I'll be presenting some of the work that we've been doing. This is at the Dublin Combustion Conference, so hopefully we'll be able to meet in person very soon. So why are we interested in carbonaceous nanoparticles? Well, carbonaceous nanoparticles grow into much larger primary particles that then agglomerate and form the soot that we see. So we would like to reduce the pollution that's formed out of internal combustion engines and furnaces. It's also very interesting to consider these as interesting new materials. So if you extract these nanoparticles, they actually make interesting fluorescent dyes. And by changing fuel composition, other groups have shown that you can form different colored fluorescent dyes. Something that has also been talked about recently and is a very interesting new direction is whether you can actually create hydrogen and also carbon blacks through some sort of plasma thermal process. And so it'd be very interesting to know how nanoparticles form so that we can make more of this carbon black and hydrogen as well. So let's just go into a schematic that I've recently prepared, looking at the progression of fuel to particles. And so you can see at the bottom here, you've got these small pyrolysis products that then cyclize into ring structures that grow through acetylene addition into these large aromatics. And these large aromatics I've taken from high resolution atomic force microscopy work you can see on the right here. And this was done with a carbon monoxide tip able to resolve the bonding network and some really quite remarkable results there. And of course, you get these nanoparticles forming that then grow into primary particles, which agglomerate. But not only is this is just not very well understood at the moment. So it's the dark zone. And what we're interested in is understanding how these molecules cluster together to form nanoparticles. So previously I've discussed in publications a lot around curved aromatics. And these curved aromatics have some interesting applications when it comes to the electrical aspects of combustion. But today I'd like to focus the talk on looking at some chemical mechanisms that can drive soot formation towards these nanoparticles. So I'm going to talk about these molecules here. And the first thing that I did is I wanted to consider looking at the reactivity between all of the different types of reactive sites that have been, that was recently resolved and was presented at the 2019 in the symposium. So in order to do that, what I did is I got all of the different types of chemical reactivity, the radicals, but also the closed shell species, and I considered the reactions between those. And so this is the first step to clustering molecules, considering how they can form thermally stable structures. And I've colored them according to whether they are thermally stable or not. And so most mechanisms for soot formation to date have considered looking at these aryl-linked structures. So these are sigma radicals, so a hydrogen abstracted from a aromatic molecule. Now we've actually done the kinetics of this and shown that, and others have shown, that the reactions between these sites are just not rapid enough to explain the rapid nucleation that we see or the inception that we see of soot particles in the flame. I think the most interesting thing we found is that the pi radicals are not all the same. So we found that there are some specific pi radicals that are highly reactive and form these stable bonds, which was quite surprising. So let's just go into a little bit more detail about them. What I'm talking about here is this molecule here. And in this case, you've got a pentagonal ring at the rim of the molecule, which is partially saturated. So one of the carbon atoms has 2 hydrogens and the other has 1. And so this is a pi radical. Now, what makes that pi radical different from a normal pi radical, which is delocalized around the edge of the aromatic network, is that its spin density is concentrated at the edge of the molecule. And as this molecule enlarges, that spin density, which is directly correlated with its reactivity, maintains its high value. And this means that unlike with the delocalized pi radicals, they actually form very strong bonds. So usually with a delocalized pi radical, it will form a weak pancake bond, roughly around 20 kilocalories per mole of binding energy. And you might be able to form a sigma dimer, which is a single-centered bond, but the molecules no longer can be stacked. However, for these localized pi radicals, you can actually form a bond while the molecules are stacked, which is unique. And so we decided to call this a rim bond for the reason that I'll explain. So it's actually a Cambridge analogy. So there's many bicycle wheels and many bicycles around Cambridge. And we can consider this bonding type to attack the rim. So imagine two wheels, and if those wheels were attached via the rim, that would kind of describe the type of bonding that we see here. And so this allows this strong sigma bonding with the physical interactions. And I guess the first question you could ask is, are these species present in the flame? And so what we did here is we created a reaction mechanism for the rim-based pentagon, looking at all the ways that hydrogen can be added, but also abstracted from it. And then by putting these edge types in partial equilibrium with hydrogen and hydrogen atoms, we're able to basically compute in a batch reactor simulation the concentration of these pi radicals, which is denoted by this dot dash line here. And we found that in certain conditions, you do get a large concentration of these, and in some cases, they can be larger even than sigma radicals. Now, if we can compare that with the high resolution AFM, and we look at the frequency of the unsaturated, the fully saturated, and the partially saturated, we see a qualitative agreement as well. So while I was actually doing this the schematic, I also drew this molecule here, which is a very interesting molecule. So let's go into this here, and this is the first time that I've presented this. So basically, this molecule here was originally drawn in the paper like this, where all of the pi electrons have been paired up into double bonds. But there's actually another way that you can draw this. And so you can draw this with an extra class sextet here, where the pi electrons have completely decoupled. And to my surprise, when we calculated the ground state of this, we found that the triplet is actually a lower energy than the singlet, which implies that this is a diradical in its ground state. And it's actually these localized pi radicals that make this possible, because the spin density you see here is very, very similar to what you see for the mono pi radical. So let's consider the types of reactions that are possible here. So when we form a bond between, say this site here and the other site, you can form a strong bond. So this is very close, within 5% of the bond, just between the monoradicals. So they react in the same way as the monoradicals in a barrierless-like reaction. But what's interesting is that this species here is a triplet as well. So the monomer was a triplet, and now the dimer is a triplet, and you can continue to add these molecules. So the trimer here has a bond energy of 230, which is the same bond energy between the monomers and the dimer. So each monomer addition has a very similar bond energy, which you would expect if these reactive sites are highly localized. And what we are wanting to name this is the polymerization of these aromatic rim-linked hydrocarbons. So then we wanted to ask, well, how do diradicals in general react? And I can go into more details, but practically how we achieve this is work that Lara Pascasio conducted. We were able to couple together meta-hybrid DFT in a QMMM calculation. So we're able to describe reactions that follow the correct potential energy surfaces, but also consider collisions between different types of radicals. So the first thing I want to show you is how sigma radicals usually react. So if you have two sigma radicals here, we find that when they do form a bond, they form a bond upon collision. So this is actually not a very common approach, as you can imagine. And so basically, as the molecules get larger, the collision efficiency or the fraction of these reactions that form a bond gets smaller and smaller. We can also consider when these molecules are stacking. So sigma diradicals can stack. However, when they're stacking, they're unable to form a bond. And this is just due to the symmetry of the sp2 orbitals that are involved. But we did many collisions and we did not find any of these sigma radicals forming a bond. So this is where the two sigma radicals are getting close to one another, and we were unable to form a bond. So they get very close, but then they just go away from one another. So let's consider now the pi diradicals. So let me show you the video for this. So you can see that the molecules are stacking together, but they're also rotating relative to one another. And for all of the reactions that we studied, many collisions, whenever these pi diradicals form the bond, you can see it forming it there, they're always stacking. So these are very unique in that when they're stacking, they can actually form this thermally stable bond. So let me just show you that again. So the two molecules coming together and they undergo this lovely little molecular dance, you could call it, until the two reactive sites get close enough. And again, I'll mention these are barrierless reactions, so they form very readily as soon as the reactive sites have reached, are near each other, and you can see that bond forming. And we're also able to show that this bond is going to be stable up to 2,500 Kelvin. And so once this bond forms in the flame, it's unlikely to be thermally degraded. So what we see here is we see this physical condensation process occur, which then allows internal rotors, which have been mentioned for a long time in the literature, probably most recently by Frank and Mabel in 2020, where the molecules condense and then they're able to rotate, and then the reactive sites are able to find each other. And we find that these molecules are able to do this below their boiling point. So, above their boiling point. So this means that the molecules are physically interacting, but there's not enough physical interactions for them to actually condense. And you can see that bond being formed. So, what I've mentioned today is looking at these very interesting localized pi radicals that appear to maintain their reactivity within aromatic networks, and those allow for pi diradicals to form, which have some very interesting properties. They can react in a chain reaction, they can form thermally stable bonds, and they can, and we think they might be quite important. So let's think about some implications of this. So the first thing in terms of reducing pollution is we know a little bit about the way in which these localized pi radicals react. So they form very weak bonds with O2, and that's because there's a partial resonance stability of these sites. So they're very hard to remove with O2. This is benzyl. However, they will react with oxygen atoms. And so there is a thought that perhaps the addition of ozone could be a way of effectively removing these sites from the flame. And indeed, ozone addition has been found to significantly reduce the amount of pollution that's formed in this counterflow diffusion flame. The other thing that's quite interesting is if you understand how this process works, you can start to consider how do we remove pentagons, for example, if we want to create graphene? And in a recent paper that Gustavo Leon did, we were able to show that this oxygen atom is actually able to etch these pentagons and allow for graphene to form in things like ethanol plasmas. And so it would be quite interesting to continue to explore this. And finally, if we can enhance this polymerization process and understand how important it is to soot formation, perhaps we can increase this for the production of hydrogen. And I'm very happy to thank you for listening, and I'm happy to take any questions that you might have. So thank you.
Okay, thank you very much indeed, Jacob. So do we have any questions? Yes, we do. We have a question from Reza, who says, thank you for your talk. How much physical interaction enhances the chances of reaction between reactive sites? And is it size dependent?
Right, so it very much is size dependent. So I wonder if I've put the slide in here. No, I haven't. But if you go to this this preprint here that's currently on the website, we've got a size-dependent kind of reactivity network. So we've been able to look at how, as the molecule size increases, the fraction of collisions that leads to reaction increases for these pi diradicals, but not for sigma radicals. So as the sigma radicals get larger, the fraction of reactive collisions decreases because it's just less likely that those reactive sites will collide and hit each other. So we do actually see a significant enhancement with size.